Hey everyone, how are we doing? It is time for some activity. If you're here, feel free to say, hey, Mewbot just woke up. There is a new command in the chat. You can now say hi to Mewbot. Say, hi, Mewbot. How are you doing, Mewbot? Hey, Mewbot, how are you doing? He'll say hi to us back. He's a good bot. We'll give everyone 100 points. He's saying hey to everyone in the chat. So if you are here, feel free to say hi. We're going to start off here. Let me take a timestamp of what's going on. I'm going to bring the timestamps to the screen. And let's go right here, take a timestamp of 6:45, start of activity. Okay, let's do this. Here we go. So with this activity right here, we are doing simple regression part 2. Regression is the idea of fitting a line to data. So we're just taking a line, putting it on that data. So what are we going to do? We're going to work with the bulldozer data set. Got my second cup of coffee today. Good stuff, coffee. And let's make the font a little bit bigger. Oh, wrong screen to make font bigger on. There we go. Way bigger font. And we can see what's going on. Use the data loaded from Bulldozer dataset. This contains information on 924 bulldozers that were sold at auction. We want to predict the selling price of a bulldozer with a sale price from its year made. You can read more about this dataset by doing $bulldozer if you really want to learn about bulldozers. So we need to load in the data. This is data that is in reg class. If you don't have reg class, make sure to install it. Reg class is currently installed on my R. This is basically like booting up a video game right here. So you can install a video game, which I've already done. It's already installed into my R. And then we can go here to library reg class, which will then load up the reg class library. From there, we run data bulldozer, and that is going to load in the data set. So that's basically an Excel spreadsheet for us right there. Cool. Got a bunch of tires and blade measurements. A lot of good stuff right here. And now we are going to load some predictions in here. Make a scatter plot. This is a lot like your assignment right here. Add the arguments this right here and this right here. Fit a regression line and give it a name. You will see the relationship does not look very strong, so it's going to be a little bit spread out. You will see that it's not very strong. However, the trajectory does look linear. We need linear models here. And does not have much curvature. So let's go ahead and take a look at this. Let's go over here and create a model. I'm going to use a trick that you may not know. The attach function attaches a data frame to the global environment. This means I can type things like sale price and they'll autocomplete. Now these are now accessible in the global environment, which means you don't see them there, but actually maybe you do see it. There it is right there. So I've got that attached to the global environment, so you do see it up there in the global environment, which means I can just type them and it will autocomplete. It's amazing to have that attached. It makes life way easier because now if I'm going to knit this, I would need that right there. And we're going to go right here and go to plot, sale price, and I think we're doing year made, right? Year made, and we can do this and it autocompletes because we've attached. That allows you to get the vectors in the data frame. These things right here are now in the global environment. So I get my autocomplete and it will now capitalize correctly so I don't have to worry about capitalization errors. We do still want to put, I think it will work if I don't do this, but we still do want to keep with good formatting and use the bulldozer right there and get the plot. Now we don't see, that's linear. You telling me that's linear? I don't know about that. Is it somewhat linear, maybe a little bit. Let's go ahead and fit a linear model to this. And the linear model can be done with the same code. We're going to store it into the object M. And I'm going to do a little reverse of the order of the code. Reason being is if we're going to use the linear model right here, we need to first make it. Like if we were knitting this, we would need to make it. Now you notice you can't see this right here. So we're going to add a col for color to it and call it, we're going to do UT orange, which is FF8200. And there's a little UT orange. We can make it look even better by going to line width. Line width equals to 2 and a lot better to see. Let's go up to 4. There we go, some UT pride right there. We can also, it tells us to add in the PCH. PCH is point style and CEX is character expansion. So what it's asking for is on the plot down here, it wants us to do PCH, which is the point style. Notice the points have changed to a different thing. And then it wants us to do CEX, which is character expansion, and that makes the points smaller. Okay, our line's got to be smaller now. And there we go. And then last but not least, we could always do something like col equals purple. It's whatever you want. Main equals, why not? So once again, you can make whatever plots you want, and this is just good practice at understanding how arguments work, and the plots will auto adjust to the screen size so you can get a plot looking the way you want. Now, besides all the fun coloring stuff, we really need to just understand what's going on with this plot. And when you look at this plot, you'll notice that the plot has a sort of bend to it. The spread around the line, which is not really going through the line that well, is meh. This whole plot is kind of not loving it. I'm not loving it. This is a regression that is in need of some help. We're going to have to fix this up, and that's the main thing we're going to be working on today with this regression. So overall, I give this a not so great regression. Hey, Kayla, great to see you here. Ask the questions in the chat if you got it. Let me know what you think about the code. We kind of expanded upon this code right here, and we created our plot. We created all this. I do want to point out that the whole creation of this plot right here is not needed because Kayla, for 100 points, do you know the easy way to get this plot right here? Because rather than doing all the stuff I did right here, we can get a very similar visualization very quickly. And Kayla, for 100 points, do you know the very quick and easy way, which I think my graders should count for? Like the very quick and easy way to visualize our model. Like it's like we can do all this, like writing this and do our own custom stuff, or we can do it like that. And how would we do it really super quickly? How would we do it really, really quickly? How would we get the visualization of this model super quick? The answer is with the code visualize model. And all we have to put in is M. And now I put the wrong letter. See, put the right letter. And so now we get a very similar plot. It's not the same exact plot, but it's still showing the line, the points. It gives confidence and prediction intervals, but it's still the same data. And frankly, it might even look better by most standards. It has a little bit different of axis scale, but it's the same data, just graphed a little bit differently with different like scale to it. But rather than doing all this code right here, which required all that work, we could have just done the following. Oh, so you can use plot. So you can use the plot function. Then you need to kind of do your colors, your point size, and all those things. And that's what we created here. But you could also just do visualize model of your regression. So this is the long way of doing it. And down here is the short way. So I kind of like the much quicker way of doing it, where we can just get everything done by just saying visualize model. The additional arguments, as we were saying right here, changes the type of point you get. So PCH inside of the plot would change the way these points look. So you notice how they look different now. And then CEX is character expansion, changing the size of the points. So you can make your points bigger or smaller in a plot. You can also change what they look like with the PCH. So those are just, yep. And the visualized model is just super quick. It's like, rather than doing all that, we can just get this. There's more customization options by using the plot. So yeah, it's cool. And so it's kind of your choice. But I think my graders should accept the visualized model. If you're ever feeling like you didn't get graded properly, please let me know. With the value of the slope right here, it's standard error, blah, 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 and p-value, all these things are only reliable when a model is a sufficient reflection of reality. Run, check, regression. Kayla, what do you think is the biggest issue with this model right here? I see at least one huge issue with this. There's at least one crazy issue with this, and we're going to review how to do the check regression. What are your thoughts? I'm going to get the notes up here on the check regression that we wrote yesterday, and this is a great review of yesterday's notes because the check regression has some steps. So here are the steps that we went over yesterday on how to do check regression. And we're actually checking the conditions down below. We're talking about the residuals. Are they normally distributed? Do they have a mean of 0, which is the linearity condition? And do they have constant spread? And we're going to see that in the conditions here in a moment. So let's put these conditions over here, zoom out on them a little bit, and try to get everything on the screen so we can see the conditions at the same time as we talk about them. And we'll get our plots going over here. We're going to decrease the size. I don't see this. I think is it due next Friday? It might be due next Friday. Some classes might have it due this Friday, so I'm doing it right now. But just here reviewing the concepts that we're doing this week and getting ready for the test 2 weeks from now. Oh my gosh. Lots of time, right? Lots of time. Let's run this check regression. Now, check regression is one of my favorite outputs to look at because if we get it down, it's really easy to understand. So we need to know how to read this output right here. Get ready. What does this all mean? So Kayla, what is the first step right here? What is the first step we need to do? So what should we do first? If you can read the small print up there, what should we do first? what should we do first? What is our first step when we do this right here? Oh, you might be... So the first step right here, looking at this right here, our instructions right here. Oh, let me remove this because this was from notes from a problem we did. Our first step right here is to do what? Our first step is to do what right now? What are we going to do first? The very first step we do... I deleted something too much. There we go. The very first step we do... There we go. Check the p-values. Kayla, great answer right there. We check the p-values. So this is counterintuitive for most people, but a low p-value is bad. It means we fail the condition because the assumption is that linearity is good until we have evidence, i.e. low p-value, it's bad. So this is bad right here. Linearity is bad. It's not going around the line, is not going through it. The data is kind of bending across the line. And this is where we look at the linearity condition right here. The next condition is the equal spread condition. And guess what? The equal spread condition, is it good or bad, Kayla? The equal spread condition, is it good or bad? What are your thoughts on the equal spread condition? Are you like, is the equal spread condition good or bad? What are your thoughts? Do you think it's good or bad? So we'll think about like test questions we could come up from this because I write test questions from this. Is the equal spread good or bad? Just looking at the p-value alone, be like, let me look at the p-value. Is that a good or bad p-value for equal spread? And so remember, if it's higher than 0.05, right there. If it's lower than 0.05, we'll continue on, which is not a good thing. So this p-value for equal spread here, this one right here, it's good. It's good. Don't worry, Sierra and Kayla and everyone, all the points. Great job, both of you. No, don't worry. Good practice. High p-value is good in check regression. It's counterintuitive. High p-value is good in check regression, counterintuitive. So good practice right there. On that, you'd be like, oh yeah, wait, check regression. That's good. That means we don't have an issue. So the other issue is normality. So we fail 2 out of 3 conditions. We fail linearity, we fail equal spread. Next, we need to look at the sample size. The sample size is greater than 25, so we can continue on. Next, we need to check the plots. How does the normality of the residuals look? So is the normality of the residuals good or bad right here? This is where we look at the normality of the residuals. It's the residuals, and if they're normal, how does that look, and what should it look like if it's good? If it's normal, how should it look? And does this look good? So this one we failed, so we're looking at the plot over here for it. How do you think that looks? How would you say that looks right there? Put a note for the check regression. It's really good practice. So we have to look at that plot and be like, does that look good or bad? And we have to know what good looks like. Good is when it follows the red line. So if we have a QQ plot, which is a normal quantile plot, that is good, it will follow the red line. Oh, really? Oh. R norm. It'll follow the red line. The more it follows the red line, the better it is. So these are all good right here. It has a little bit of an issue. It does have a little bit. Yeah, great job, Sierra, right there. It's got like these are actually coming from the normal. What we generally want to look for is you really want to see if you see something closer to this right here. You really want to see if you see something like these. These have major problems. Does that make sense? Like these are bad right here. This one is up. Did I not run it? This one is good. And this one is bad. So like good, bad, good, bad. And these are different each time because I'm using random generation. Good, bad. So we would say then, how does ours look? And overall, ours looks I'd say, I know it's got problems. It's got that problem down there. Good eye right there, Sierra. A little bit of a problem here. Mostly good. I would say not too bad. Just imagine you ask a 6-year-old to draw a line and they drew this and you'd say, that's okay. But where do you see the big problem? Where do you see the big problem, which we had another thing to check? Where do you see the big problem? The big problem is definitely, and we saw it with the original plot, so we saw it when we even looked at our original plot. What was the big problem you see right here, which is apparent here? And it's also apparent in the residual plot down here. There's definitely a big problem with what? And this is where we look for this. There's definitely a big problem with what? Like, yeah, that one's I'm not letting that one pass. Correct. And let me put those steps up here again. I think, Kaylee, exactly what you're saying right there. So what we do is if the p-values are low, which is a problem, we then say, do we have enough sample size to continue? Like if we fail any condition, we then say, do we have enough sample size to continue? If the sample size is not large enough, which this one is because of 924, if it's not large enough, we just stop and we're done. But if the sample size is large enough, we can continue on to the third thing where we actually look at the plots and make our decisions ourselves. And does that make sense, Kayla, right there? I think both doing a great job. And this right here does not pass linearity, I'd say. Like this is a swoosh right here. That's not good. You don't want it going up, around, and down and back up. That's not a line that goes well through the middle of that data. So the linearity is our biggest problem right here. The linearity, I would say, is our major problem, and we're fitting a line to this, so the line idea is kind of important. So that's kind of not good right here. So we figured out which ones we failed. We know our model is wrong. So let's say here, failed, really bad plot. I'd add more. I'd talk about it a little bit more. Equal spread, passed. We don't need to say anything else. We passed it. Failed. Kind of bad plot. I mean, it's kind of bad, kind of good. We're talking about this plot that I was blocking. It's kind of like, it's like, meh. It's kind of bad, kind of good. I don't know. It's not horrible. We've seen worse. So the one to really worry about is the linearity. The one I'm pointing at right now, the normality plot, is not so bad. It's like, it's okay-ish. I'm really worried about this, though, and it's concerning to me. And in my opinion, Dr. Petrie's opinion, it takes years to figure out these plots. Well, maybe I've built up that experience to have that intuition right here. So what we're going to do right here is we are going to have legend appear in the top right. Look, additional information. How many should be outside? Okay, good. So this one, in my opinion, I'm trying to remember what this one asks. How many should be outside of 924 hours actually close? Tomorrow's are estimating the relevant. An additional informal test of the model's validity check to see whether about 95% of points fall inside of a prediction interval. Okay, let's look at that. I was like, wait, what are we asking again right here? Okay. The prediction interval is the wider interval. The prediction interval is for individuals, where the confidence interval is for the mean. Huge note to have. Let's put a note right here. Predictions versus confidence intervals. So this is a big note to have and is at the end of this assignment. If we're talking about a prediction interval, prediction intervals predict for one individual. Confidence intervals predict the mean for all individuals. Confidence intervals are always going to be tighter than prediction intervals. So the prediction interval has more variation in it. And we can see what points are outside of it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37-ish. And let's see right here, this is 95%. Out of this many data points. So I said 37. 37 divided by this, that is about 4%. So the complement of this is very close to 95%. So interestingly enough, the 95% confidence intervals encompass about 95% of the individual points. So you would expect some points to be lightly outside of it. This is a 95% confidence prediction interval, 95% prediction interval, last stats 201, where we are predicting the price of an individual bulldozer. So if your friend wanted to buy a bulldozer and they said, oh, it was made in the year 2000, would you use a prediction interval or a confidence interval to tell them how much you think it'll cost when they go to buy it? Your friend wants to buy a bulldozer. Would you use a prediction or confidence interval? Take a moment in the chat right here. This is a good test question. Now, it's a little counterintuitive if you took 201. Your friend wants to buy a bulldozer. Would you give him a prediction interval or them? Oh, Brendan. Don't worry, Brendan. Prediction intervals are for what? And confidence intervals are for what? 100 points right there in the chat. Thank you so much, everyone, for being here. Confidence intervals are for an average of all bulldozers. Like if they wanted to look at the market, so the way to switch the question is to say, your friend is some sort of like bulldozer, I don't know, kingpin. And exactly, Brendan, you see it now because it's one. Since they're buying a bulldozer, that is for one individual or for one observation. So that's going to be what we expect. Like saying, I predict one bulldozer will cost between this much. But then if we're talking about like the market right now, the average price of a bulldozer in the year that was made in the year 2000 would be contained between here. And that's the average. That's the very small interval, which the mean has less variation in it because the mean is like based on all observations, where the individual is like, there's a lot of variation with one individual. Like, I don't know what conditions the bulldozer in. We're not talking about like the law of averages where things kind of average out. The law of large numbers, like over long trials, we'll see things go towards the mean. Central limit theorem. Lots of great topics. Good stuff. That's a good question. Didn't think about it. Like, very good. So now we're going to predict how much our friend's bulldozer will cost. This code right here will be on the midterm, and you'll be expected to write it. Does anyone know what this code creates? Let's put a note right here because this is going to be very helpful for the midterm. People will need to know about using the predict function. So what does this code create right here? What does this code create? What does this code create right here? It creates a what? So it says store into the object to predict. So you can just call it whatever, TP to predict. Store into the object to predict, TP for short. A what? And that's what it's creating. That's what it's actually making. And then that has a vector inside of it. So it says store into TP the data frame with a vector year made with the information being this. To see how the data frame function works, just try writing a data frame right here and do the following. Make a vector inside of it 1, 2, 3, and put another vector inside of it 4, 7, 3. And there's your data frame. You could give them names such as like variable 1, and you could give them names such as variable 2. This is good practice to understand what these codes are doing, that this is just creating a data frame with one vector inside of it, as in this will be the vector right here. There's no second argument vector. This is literally just the only argument. So I've separated out my vectors in the data frame like that, so you can kind of see right there what's going on. Understand what your codes do and be like, okay, I'm making a data frame. I'm storing it into this object. So then when we run it right here, we can see this. And let's go take a look at it. Here it is right here. And there it is. So it looks just like what I created on the screen. It's just creating those vectors or that vector into a data frame of values. Now, why is, and I want one letter in the chat, why is that going to be very important for us to use to predict with? Why are these values very important for us to use to predict with? Hey, Adam, great to see you here. Why are these values very important for us to predict with? I want you to look at what this is, and I want you to think why these are very important for us to do predictions with. Kayla, great to see you here. So why are those values very important? 100 points, everybody. Why are those values so important for us to use to predict with? What do you notice why we would use these values right here to make predictions with the line? So when you think about your line, why would those values up there be very important? Those values are the whats. Why would those values be very important? They're the X's, exactly, Kayla. So you know what's really amazing? Check this out. The X's, and they explain. The year made explains the sale price. What's so amazing, and I try to tell 201 this all the time, is that we're not here to solve math equations. We're here to learn how to solve stuff even faster. What do you think predict will do if I put my model inside of it? It'll give me what's from my model. What do you think the function predict will do? Now be careful, because this is where sometimes people get two codes confused, and I'll mention the two codes here in a second. But the functions usually do what they say they're going to do. And I'll mention the function that's confusing for a lot of people here, where the overlap in knowledge happens. So what do you think predict will do if I give it my model? It'll probably do what? And I'm pointing at the red line. It'll probably give me the whats. And it'll do it for all the data points. So if I use the predict function, it'll predict for me just, whoa, it did all the predictions for all the observations in the model. For all 924 observations, those are the predictions. But what if I have new data? What? Oh, TP. Now it's making predictions for the what? If you see right here, we have a bulldozer made in the year 1965, which is over here somewhere, and that's negative. Oh my gosh, because that's 0. It's making predictions for the what? I say predict using my model and predict on the new data. It'll make predictions on the new data. So I could change this right here and say, get me a bulldozer from the year 300, and that's ridiculous. So all it's doing is it's taking the model and plugging in the value of year made and solving it. Does that make sense, Kayla, right there? That all it's doing when I run this is it's saying make predictions using the coefficients in the model. Like it solves it for me. It plugs in the value of X, whatever I put in right here, and then solves. So I can put in crazy values. I'll get crazy predictions that are extrapolations of the model. But this is just going to use those values and give me the predictions related to each one of these. So this is the prediction for a bulldozer made in 1990 and the prediction for a bulldozer made in the year 2010. So these are all the predictions. But there's one additional argument, and this is where the confusion happens. The following argument is interval equals confidence. And this just gave me what for those intervals. Will give me what for those predictions. So now I have what for those predictions. So this whole function right here, predict using my model on new data, give me confidence intervals. I just have what? If you look, this is the first bulldozer's prediction, the fit from the model. That's what the fit means. That's the prediction. And then the confidence intervals are right here. You can see they're still negative. Those are the confidence intervals. The thicker band line is the confidence interval. So it's doing it right here. The second bulldozer was one made in 1990. So it's over here. The prediction's over here. So that's the 5,000 or 59,000. And then it's a very tight interval because it's towards the mean of the data. And you can see that interval right here. And that's that little tiny band. The upper and lower confidence intervals for what we expect the mean bulldozer price to be of a bulldozer made in 1990. We can change this right here from confidence to prediction, and now I get the wider intervals. So if you notice right here, this is if someone buys an individual bulldozer. Where did I write that? Here we go. Prediction intervals are for one bulldozer. So this is predicting a bulldozer made in the 90s. Remember, the second value in my my data set right here is a bulldozer made in the 90s. So this is, we expect a bulldozer made in the 90s to be about $59,000, but I'm 95% confident this individual bulldozer will be between these values. Very wide range, and that's what you're seeing right here. That's the lower value, and that's what you're seeing right here. So it's finding you these values very quickly and very easily. But this whole confidence interval talk, what do you do? What do you type to open? Oh, the shiny dashboard thing? Shiny widgets. Are you talking about this right here, Adam? I'll drop that in the chat for you right there. That should do it right there. That'll get you shiny widgets. Yay! If that's what you're asking about. Good question, Adam. And so with this right here, this code is oftentimes confused for confident. Confident, so don't confuse the two codes. It's a very common confusion. Confident gets you confidence. Great job, Adam, right there. Confident gets you confidence intervals for the what and the what. So just repeat after me. Confident gets you confidence intervals for your what and what. So look at the code. Tell me what it's doing. Confident is getting you confidence intervals for your what and your what to estimate the values of what and what, which that is about the least interpretable thing I've ever seen for that. Gets you confidence intervals for your intercept and slope. So I oftentimes see confusion on this one because it does mention right here a confidence interval, but that's a confidence interval for the mean at these points, the mean right here of your data at the point. So these are different confidence intervals, but a confidence interval for the slope and the intercept. You notice the slope is positive, so we do think there is some sort of relationship between the year a bulldozer is made and the sale price of said bulldozer. So we've got right here, obtain a 95% confidence interval. I think we might have done this one already. Obtain a 95% confidence interval for the average sale price among bulldozers who have those 3 years. Oh, we did that. Obtain a prediction interval. We did that. Additionally, observations, the widths of. Yep, so it's a little bit of help output right there, explaining it. Make a scatter plot to visualize the relationship between sale price and usage. So now we need to go with sale price and usage right here. There's clear problems with the residuals fit. The regression model and run check regression to see where those residuals. Okay. So I think we're going to do a little transformation run here. Find transformation is good. Okay, so let's go ahead and fit this model right here. We are going to fit sale price with usage, and we need to do data equals bulldozer. And now let's go ahead and visualize this model. And there's the visualization of the model right there. So we got the model visualized. Yeah, it's got some weirdness. So we've got the fit, and let's do the check regression. Are you ready? Here's the check regression, and this is the good practice. So let's do check regression of second model right here. And let's mark that in the notes. Check regression of second model. Oh my gosh. Check regression second model. Where do the big problems look to be at? Where do the big problems look to be at? Ooh, I see the biggest problem. Can you spot the biggest problem? Go through step by step if you want right here. So take a moment and try to solve the biggest problem. What is the biggest problem? So how many problems do we have? I'd say, I mean, you can look right here. So where do you see that plot? 1, 2, or 3, Brendan? Brendan, 500 points. Where do you see that? Don't worry. This is a really important thing to see. And so I'm throwing big points out here because we'll notice something. All of them is correct, Kayla. All of them is correct. Brendan, you are correct. Plot 1 is the right answer for where we look. And I don't really see the linearity. The linearity actually looks kind of decent, even though it fails. There is problems with all of them. Look at the p-values. They all are bad. They're all below 0.05, so we have a problem. The sample size is greater than 25, so we can continue. But now when we look at the plots, I'd say my biggest issue is where? Is it linearity? Is it equal spread? Or is it normality of residuals? What do you think is the biggest problem right here? There might be a secondary one, you might say, but it might be due to lack of data. But what's your thought on the biggest problem here? What's your thought on the biggest problem? Biggest problem. Which of these look to be the worst? The linearity, the equal spread, or the normality of the residuals? Sierra, great answer right there. Another 100 points, Sierra. Great job. The normality of the residuals, I would say, because remember, it should follow the red line, and we're seeing a lot of deviation down here and a lot of deviation right here. They all fail the first step. Sample size greater than 25, so we can continue. I think the problem is spread. Spread's also kind of bad too. Kayla, great answer right there. Another 100 points. That would be my secondary concern. It might just be due to less data. Shout outs to Dr. Me right here. If you have less data, you have less spread. So maybe it's due to a lack of data that we don't see much spread right here. There's just more data right here. This is a little concerning. I do agree. I also see a big problem right here. That one's very apparent. I don't really see the linearity. So the linearity, the first graph, and let me repeat here. Are you ready? If you're looking at linearity, first graph. If you're looking at equal spread, first graph. If you're looking at normality of residuals, third graph. What do we use the histogram for? Who knows our favorite saying in this class? You can have Mubot say it. I can't remember which quote it is right now. But who knows our saying about the histogram? So let's take a note right here. Who knows the saying from our class about histograms? What do we say about those histograms right there? Oh, you got it right here. Don't look at the histogram. Don't look at the histogram. Don't look at the histogram. So this one over here is the normality. And this one is the line, and the line being this. And the equal spread. And there might be a little bit of a, like, it could be due to lack of data. Don't look at the histogram. Don't look at it. So we look at the QQ plot for normality. If it follows the red line, it's normal. The more it deviates, which we do see deviations, it's not normal. So the line and the equal spread in the first graphic, and the normality is in this graphic. But Kayla, great job right there. And Brendan, great job. And Sierra, excellent work. Really good practice on remembering how we look at this. Yeah, no, this, I think it helps to draw it out right here. I realize when I see things in my head, I need to write it down. Like, I think that helps a lot. And the line is the line on my, the line is the line. Yep. This line right here. But you see a lot of people think, and Brendan, great job. A lot of people think that this line is the line. No. This is the line of normality. That line right there, that red line, which if you look at the histogram, you'll notice that the red line, if you look at this, the red line on the histogram is also the red line there. It's like I didn't, yep. So that red line that's fit onto the histogram is the fitted normal. And if you notice, it has problems. If you look at its problem regions, it has problems here, which is here, and has problems here, which is here. Those are the problem regions on the far sides where it's not fitting. But remember, bin widths, the reason we don't look at the histogram is because bin widths are deceptive. The normal probability plot is always graphed the same way. Bin widths are deceptive, so we don't look at the histogram because it's not a great way to visualize things. I don't know. I've deleted it out of the output before. I could do it if we want again, but I've actually removed it sometimes. Oh, I'm sorry. Stop. Kayla, what are you doing? Kayla, 100 points. Stop. Don't look at that. What are you doing? Don't look at that. Don't look at the histogram. What are you doing? Okay. So here we are with some visualizations with some what we can do right now is we can transform this data. So what does it mean to transform? Well, if you're going to transform data, think about this. Imagine everybody's money in here was log 10'd. It would be not fun. Because let's say Jeff Bezos walks into the chat right now. Jeff Bezos, way richer than all of us. $213 billion, Alexa just said. I was yelling at Alexa. I have to yell for her to hear that. So you ready? $213 billion. Thousand, million, billion. There's Jeff Bezos' money. If you said, Jeff Bezos, I need you to pay off my house, he would say, oh no, I only have that much money left. If everybody at UT said, Jeff Bezos, buy us a house, and Jeff Bezos bought everybody a really nice house, he would still have so much money that it is incalculable. So it's still pretty ridiculous, his amount of money right there. But that'd be pretty nuts. Oh, he actually had to spend like $10 billion or something. Yeah, so he still bought, I don't know, how many people in Tennessee? Oh, he could buy like 1 million people a house. Oh, no, he ran out of money. Okay. But watch this. What if we log 10 his money? Sorry, Jeff. We log 10 his money. Now he has $11. Maybe you only have $100. You have $2. What does logging data do to extreme outliers? If you have an extreme outlier there, now we have 2 and 11. So what does logging data do to extreme outliers? Logging data will what those extreme outliers? Just think about what the logging of data will do. You take data and it has extreme outliers and you log it. What is it going to do to those extreme outliers? What is it going to do to them? So it just got an extreme outlier there. Now you have someone with $100 has $2. Someone with $213 billion has that. It brings them in. It pulls them in. So we have many different ways to transform stuff. But watch this. Find transformations. What do you think the find transformations function does? Because we can manipulate our data. Log 10 Jeff Bezos. Can we? Am I allowed to make that for the Stats One channel? Log 10 Jeff Bezos. Yeah, that'd be funny right there, Brendan. That'd be a good shirt for people who like people like, what does that even mean? Like, yeah, log 10 Jeff Bezos. Come on, what do you don't get about that? So what we're trying to do is we're trying to like fix our data with this. We find transformations to try to fix our data. It gets mad because the graph is too large. If the graph is too large, we run it. This one, does the transformation help? Well, if we don't use a transformation, the R squared is only 1%. This means only 1% of the sale price is explained by usage. But let me do something a little bit different. We really like to use find transformation for models where transformations might really help. That first model up here, this model, which I'll call M2 at the time being, this model right here, let's run find transformations on it. If we have no transformation, oh my gosh. If we have no transformation Oh man, neither of these are good. Googling Jeff Bezos. Neither. The first one was actually better. What do you notice about when we transform the data? This is with no transformation. This is the best transformation. How do these look? This is not good. This is not worth it. Neither of these are really worth it. And I'll tell you what I mean by that. Because if we transform data, I'll get one that works right here. I know one that works. Okay, let's go grab the data ex3 abalone. Okay, let's go grab one that works. Because neither of those are good. This, what do I mean by not good? Can anyone decipher? I'm like, yeah, this didn't really do anything. That's exactly it, Brendan. It's like, yeah, that didn't really do anything to it. Didn't really do much. Not that good. It looks the same. No transformation, highest R squared, so not really worth it. Let's get one that works now. Let's do here meet weight, meet.weight, and tilde diameter. I think this is on your assignment. We're doing a little today during office hours. Data equals ex3 abalone. And there's our model. And let's first visualize it. How do you think that's going to do on the conditions? High or low p-values? Take a second right here. High or low p-values? For the check conditions, for the check regressions. Your check regressions, high or low p-values. Your thoughts? What are your thoughts on the p-values on this one? I'm going to run the check regression on it. I'm going to run check regression on this. What do you think the p-values will come back? Super high, super low? Here's a hint. What do you think the p-values will come back?
They'll come back low. Let's look at the p-values. Low p-values. Those are low.
That's some low p-values. I think we can go even lower, right? Low.
No.
It's as low as the voice goes right over there. I forgot I haven't one even lower. Sounds like graveling. So, very low. This has problems everywhere. This is just not linear, not equal spread, not normality of residuals. That's major problems here on the high side, like especially that extreme point up there. That's not following the normal pattern. That sounds like you're still right now. I had leftover rice with carrots and some tofu chicken nuggets. Good stuff. So, it sure ain't linear, that's for sure. So you know what we should do? Maybe we should look at some transformations of this data, because watch this. You want to see some magic right here? I'll show you some magic. Fun transformations. Now that's what our data originally looks like. And now with finding transformations, our data now looks, oh my gosh. What do you think about the new find transformations data right here? This is your assignment. Whoa, this is what it first looked like. And now it looks like this. Amazing. This is the highest R squared. So we see right here, let's erase it so we can see just that. And so here is the highest R squared obtained. I know, it looks pretty linear to me too. I agree. Pretty linear. And so we have an R squared now of 95.7%. Very good. So what it does is, great question, Brendan, right there. It's a really cool function. The find transformation function, let me clear this. The way it works is it does a vector of transformations, trying out all different transformations, and it stores in the best transformation. So it actually goes through and does like a loop right here and finds the best transformation. So it's going through and trying every power of X and every power of Y. So it's going to do a loop where it tries like each possible way to take your X vector and Y vector. So what is it doing with this loop? Like, what do I mean? It's doing a loop, like trying to transform X this way, trying to transform Y this way, trying to transform X this way, trying to transform X, Y this way. It would take your variable, like on ex3 abalone, and it would go right here to like the meat weight, and it would say raise meat weight to 3. And then it's going to take the ex3 abalone, it's going to take the diameter, and it's going to say raise diameter. Oh my gosh. It's going to say raise diameter to the first power. And then it creates a model from this. And then it does it where it raises it to second and does the other one and does a model with these. So it's trying like all combinations of transformations. So it's changing your vector, even doing like log transformations on these where it does log 10, which is that's how you can know it's in the output when it says like is log 10 there. It is trying to transform your values and see if it can somehow create a relationship where I can square it, root it, log it. So it's looking through all different types of transformations. And then you can see right here the transformations it tried and the best ones. So these are the best transformations it could find. And so it found that raising y to the negative 0.75 power. So I think our y value was, so I'll show you how to do it right here. The y value being this is we are predicting meat weight. So meat weight needs to be raised to that. And the x value being this. So we would have this right here. This is raised to this power right here. And we're going to call this the y transformed value and the x transformed value. Does that make sense right here, Brendan? Does that make sense that this chapter... Oh, no, Adam. Send me some stuff. You remember, you only need a prototype tonight, so you don't have to have it working tonight. But send me some stuff if you want. I'll be looking at it here a little bit later. I'm going to take a break here a moment. And then, but does that make sense, Brendan? What it's doing is it's going to try all these different possible values. It's doing all the regressions itself. It's finding the R-squareds. So what we can do now is we can make our model with the Y transformed. These are just stored to the global environments, so they're just out here. And when we make this model right here, don't worry about that, it's graphical error. Guess what we will see is we will see an R-squared of 95.7 because that was the R-squared we got right here of 95.7. So I literally took the Y power it said to raise it to, and I took the X power it said to raise it to, and then I made the model of the X and the Y variable, and then I found the same R-squared. Now, these are transformed things, so they don't have the same context. We probably won't interpret it anymore, but we do have 95.6% of the variation explained. And if we visualize our model now, we see that model we had a moment ago. This is the model up here in the top corner with the highest R-squared. You can see the 3 points over here in the kind of little bend. And if you take a look right here, there's the 3 points and the little bend. I think the point's right there. It's hard to see. But you can see the 3 points and then 2 points behind it. There's the 3 points and the 2 points, little tail going down right there. And 3 points, and there's that tail going across. There's 2 points there, and there's the 2 points there. So hopefully you can see that we're making this model that we see here as the best R-squared chosen from us from the transformations right here to raise your Y to this, which I did, and to raise my X to this, and I stored them, and I created the new model. So this is how you create your transformed model. So guess what we're going to do? We're going to see if this model is good, which I think is the last question on here. How many conditions does my model pass? Oh yeah, send it to me, Adam, and I'll take a look here in a little bit. How many conditions does my model pass right now? How many conditions does my model pass? And this is where, as Petrie said, it can take a little bit. So first off, the easy question is the p-values. This is something we should all get good practice on this, but the p-values, first off, how many of those p-values does it pass? Like if we look at the p-values, how many of those p-values are good? None. Can we continue on? So this is the transformed model I'm looking at. It's the new one. We fixed the little swoosh Nike thing that we had problem-wise, but it still fails all those over there. I think it failed all of them last time too. But what do we do next? We look at the sample size. The sample size is greater than 25, right? Tell me this. Where's the biggest problem now? Where do you see the biggest problem? Who knows the biggest problem in this? What is the biggest problem? Well, I'm always trying to throw out different people getting 500 points. And Caleb, I just want to say, I think a lot. Man, I need to give Caleb 500 points. Such amazing answers. I want to make sure you get those 500 points right here. 500 points for the whole class right there. That is the right answer. It is that third graphic with the normality. And just keep those answers rolling. Keep them rolling in. Always trying to pass around all the congratulations, and that is the perfect answer. It is the normality of the residuals right here. This is the worst one. But here's the thing. If you have a friend who drives you 95.65% of the way to New York, are they a pretty good friend? You have a friend who drives you 95.65% of the way to New York. Yeah, no, right? If you have a friend who drives you 95.65% of the way to New York, I'm always like, when I click like a 50-point button, I'm almost going to be like, wait, did he give me 50 points? And wait, didn't give 100 points. I don't want anyone to like second think things. I'm always like, I just need to get all the points I can. How would you feel about a friend who drives you 95.65% of the way to New York? But they're gonna if it's not for prison, they're gonna smoke in the car or something. This is a problem. We don't like this. I had a friend who we went on a car trip and they smoked, and smoke if you want. I'm not a big fan of smoking. But this is a lot. That's a lot. That does a lot for us. 95.65% of the variation explained. How's the line doing over here? Is that line going through the data pretty well? How's the line doing? Ooh, but I do kind of see a little explosion of points. I don't like that. How's the line doing? Which we're trying to fit a linear model. If you remember, the line looks like this. How's the line doing? So you can look at it there, or you can look at it here. How's the line doing? Is the line going through the middle of the data? Your thoughts? Exactly. Oh. How's the line doing? Does the line look like it's good or bad? Now, the line does have a problem according to the test, but then we have to look at the plot and we have to decide for ourselves. I'd give that line a B+. I'd say I don't see many problems. Apparently, you have a problem. So it should the points should be an even scatter. It should slice through the middle of this. Imagine this is like, so Kayla, you have to imagine like this is a cookie, and you're gonna break it in half for your kids, and one kid's gonna get this cookie right here, and the other kid's gonna get the other side of the cookie. I should draw on it. So you want to cut it. You want to break it in half. You want to be like, I am going to, if the line is good, then this will be one half of it, and this will be one half, and it will kind of be even on both sides. Now, don't worry about the spread. Don't worry about the spread. It should be like even on both sides. You should like be able to break it in half, and the line should be cutting down the middle of it. The spread here doesn't matter.
It doesn't matter.
What matters when we think about the line is if it goes through the middle. So there's some good examples in 201 we've been talking about with Patrick Starr. There he is. This right here is a very good linear model, but the spread is not good. So there's a sad Patrick Starr because the line goes through the middle of the data. It would cut Patrick Starr in half. Does that make sense right there? Like if the line goes through the middle in the residual plot, it should look through the middle. So this is a residual plot too. You're looking for the symmetry of it exactly. So this right here has problems with the equal spread, but it does not have problems right here. We did a thing where we differentiated it too. It's funny because a lot of what we're doing 320 right now is covered in 201. So it's a very good review, very good practice, and that's why I really like when people take 201 and 320 because we get to do a lot of the same concepts. Oh, here we go. Whether we're plot thickening and stuff. Where did I did another drawing today? I don't know where it went. But the Patrick Starr one's really good right here. Like we're trying to slice Patrick Starr in half. Sorry, Patrick Starr. And if we slice him in half pretty good, like that's a pretty good slice down the middle. Yeah, exactly. It's like how upset would they be? And a really good example of a non-linear relationship would be something like if we had something like non-linear residual plot. So what you would get right here is if you have a non-linear relationship and then you make a residual plot from it, you're going to see something in the residual plot like this, and this is not good. So you might say, well, it is about 50-50 because that's what residuals will do, but you don't have that idea of symmetry on it. Like you don't have a symmetric relationship. So, or we should do, like here's where the data's at, but we don't see the symmetry on the other side of it. So this right here has a lack of symmetry where whatchamacallit, Patrick Starr right there has pretty decent symmetry. Like he's not perfect, but for the most part, he's pretty symmetric on both sides. Yeah, close enough. That's what we do. It's like, it's pretty good. Yeah, it's pretty good. But would anyone ever look at this plot over here and say, that normal probability plot, it's pretty good. What are your thoughts on this? If you said draw a straight line to your kid, you got to pretend you have like a 8 or 9 year old today. So if you said draw a straight line and they turned this in right here, you said draw a straight line. How would you feel about that? You said draw a straight line, draw like straight line. And they did this with the points right here. You'd say, how would you say? Would you say, that's pretty good? Say close enough. Close enough. You tried. Would you say, what are you doing? You'd say, oh my gosh, what did I teach you? That's not a straight line. That's horrible. What are you doing? Yeah, it's really bad. That's really bad. So that's where it's pretty crappy. That's what it is. I'm sorry, son. That's pretty crappy. Man, Dad, you're mean to me. Oh, don't worry about it. Just let me do it. Just let me do it. I'll draw the straight line. And then you know what we do? We'd go over here and we'd go, Watch this. I will draw you a straight line. How did we do at our straight line? Frankly, we might have done what? How did we do at our straight line right here? How did we do? How you say, oh my gosh, what is going on? Then we call in the reinforcements. We call in grandpa and grandma. Grandma and grandpa say, I know what's a straight line. There we go. That's a straight line right there. We did worse. We did worse. So this, the less it follows it, the worse it is. And that's really not following it. It's a bunch of weirdness. You see, the histogram doesn't do it justice right here. The histogram, there's a lot of outliers, extreme points like down here, especially extreme high points. It's probably, that was my dad's try, not mine. So we don't want normal probability plots to look like that. That comes from an exponential. This comes from a normal distribution. If it follows the red line, it's good. If it doesn't follow the red line, it's bad. And so we failed the test, so we had to look at this. And the only ones I'd say we're kind of good on are equal spread. I'm a little worried about. Linearity, I'll give it a pass. But normal probability plot, I'm saying it's bad. Plot 1 is King Solomon approved. Yeah. There's a really good... there's a Recess where they spoof that. Gus becomes king. If anyone ever watched Recess growing up, I've seen every episode like a billion times. It's kind of scary. But Gus becomes king, and like this girl has a doll, and she's like, the two girls are fighting over it, and Gus says, "We'll cut the doll in half, and both girls can have one half of the doll." And the one girl goes, "Oh no, please, just let her have it. No, don't do that, please." And Gus says, "Sure, okay, the other girl can have it now." And Gus was like, and they're like, How did you know to do that?" And he's like, I can't remember. Oh no, see, I haven't seen enough. But yeah, they spoofed that right there. Recess is so good. Who's your favorite character? You know what's really funny? Do you know, if you ever watched Californication, the voice of, I'm pretty sure it's Spinelli. I think the voice of Spinelli is the voice of Bobby Hill, who is it no, it's, what is her name on Californication? Saturday mornings, yeah, Recess is good stuff right there. But Spinelli, I think, is Bobby Hill, who's also starts with an M. Marcy. She's Marcy on Californication. So Marcy, I'm pretty sure. Let's look up that actress. She's a great voice actress. She also played someone else in a recent cartoon I was watching. Oh, she did a voice in The Oblongs. She did the young son in The Oblongs. Milo. She does a lot of young male voices. Marcy, Californication. Really great voice actress. This is Marcy Runkle. Pamela Adlon. Alden. But great voice actress. Her Wikipedia right here. We'll end off class with this. That's the voice. Yeah, check her out. She's a really great voice actress. Voice of Bobby Hill. There's Bobby Hill. Recess right here. Oh, she did Spinelli. Did I say Spinelli? I think I said Spinelli. Time Squad, I don't know that. But she did a bunch of but Bobby Hill, number one right there. There's the voice of Bobby Hill. She was in Californication, but she's really great right there. She's got a lot of it's really great. She was in Grease 2, Say Anything, Bed of Roses. You sent me the first, awesome. All Square, Bumblebee, Holler, but no, really good stuff right there. But yeah, like just the voice of Bobby Hill. It's one of my favorite jokes. Did anyone here? This is my last comment here, and then I'm gonna go and take a break, and then I'll come back at him. I'll take a look. Did anyone here watch King of the Hill growing up? Any big King of the Hill fans? Bobby Hill has one of my favorite jokes on King of the Hill. He was just such a fun, lovable character, and one of my favorite jokes from Bobby Hill. You have to go watch the scene. Totally ruining it a little bit here, so spoilers. Don't listen to me if you don't want to hear the joke. Yeah, I did all the time when I didn't have cable. One of my favorite jokes is Bobby, I think, has to take he's taking like a self-defense class, and oh no, but they oh man, it's just like, you got it. I don't know. Would I get in trouble if I played the WD-40 joke from King of the Hill? There's a WD-40 joke where Hank Hill can't get his propane accessories. Hey, that's my purse. That's my purse. Bobby Hill. Oh, I love her voice acting. She is so good. Okay, well, no, the joke is Bobby Hill is taking a self-defense class, and they teach him in the self-defense class to yell, "That's my purse," and then kick someone. And his dad, Hank Hill, has him put on gloves. And so they're boxing, and he's like, "Come on, Bobby, show me what you got." And he's like, punch him in the face, and like his camera just like goes and, he just keeps popping him in the face with his gloves on. So I mean, like, it's, if you want to box something, that's all right to do. But I mean, it's not that fun getting punched in the face even with gloves on. So Bobby just yells out, "That's my purse," and he just kicks him. It's just the best one. Oh, it's like, oh no, no. But the WD-40 joke is classic too, where Hank, I feel like I'm gonna get copyright claimed if I play that. But yeah, you should watch it, Kayla. Look up Bobby Hill self-defense. But I really just am a fan of her voice acting with Spinelli from Recess, with Bobby from King of the Hill. I haven't seen Milo and Murphy, but really great voice actress right there. It's not about just like doing a voice; it's about bringing a character to that voice. Oh, thank you. Well, it's really I love people like this who create amazing, interesting characters. Even Spinelli on Recess is a very interesting character. There's a lot of depth to Ashley Spinelli, one of the Ashleys, and just finding out, like, what is her parents spies? They went a little bit crazy. This thing, yeah, opens the can of WD-40 with he's got like a mini can, like, so Hank's like grabbing, he's trying to get into this door because they're at like a vacation home or something, and he's like trying to get the cap off his WD-40. He's like, dang on it. And he pulls out a mini can of WD-40 and shakes his mini can of WD-40 to spray the big can of WD-40 to open the big can of WD-40. So Hank uses WD-40 to open a can of WD-40. And it's just there's no like, I like humor like that that's so dry and stuff like that. If you want to see a good dry humor show, check out Home Movies. Home Movies is a cartoon. They used to be on like Adult Swim, but it's where usually like, it's almost like the kids are more adults than the adults, because the adults, they don't act like adults all the time. So it's kind of interesting to see how the kids are. It's really Jason and stuff. Yeah, Hank Hill's voice. Who did the voice of Hank Hill? I should know that. When I see it. Hank Hill's voice was done by Mike Judge. No, wait. He did that? Is Mike Judge the creator? He created Beavis and Butthead. He did the voice of Hank Hill? No way. What? It's interesting looking at all he created and Mike Judge did. That's interesting. Very interesting. Very interesting cast. Peggy Hill. I don't know much about Peggy Hill. Voice actress. Bill Dauterive. Luann. Bobby Hill. Dale Gribble. I'm afraid looking at random people right here. Oh no. There's Dale Gribble. Man. Craziness. Well, I'm going to take a quick break right here. I'll be back answering some emails, but great work, everybody. I think we finished off the assignment. We got a little sidetracked at the end right here. We did the fine transformation. We fit the transformed model, and yeah, we did it. We fit the transformed model. We took a look at it. That's got it. I'll be back here in a little bit. It's almost spring break. Adam, I'm going to take a look at the model here in a little bit. I will be back. So until then, keep drinking coffee, even late in the day. I don't know what I'm doing. You regress. You too, Brendan. You too, Kayla. Have a great one. Adam, I'll check it out. I'll see everyone here in a little bit. Puppet Shark, say goodbye. That's not a goodbye, Puppet Show. Digress. I do digress. Bye, everybody. Bye.